Okay, hello everyone. So how about your quiz last Tuesday? Yeah, is it quite difficult for you, or it's just okay? I've checked not all, but maybe only one third, I think. Yeah, but the score I think is quite interesting. So some is maybe around 50, others around 80. So and some below 50. So I need to check whether at the level of the basic for especially for polar curves. Uh, I think mostly uh, you understand the basic, but I think to solve the problems that need to uh, take some concept from calculus 1, I think a few of you still have that problem. So most of the integration, the method of the integrations, all is based on calculus 1. Like for example, if I have like, I think in the test you will have something like this. I forgot which number this is, but uh, at the middle of the calculation, you will see some integrations like this. To solve this, okay, if this is just a regular polar curves, uh, my suggestion is to approach this with the double angle formula, okay? Or whichever you want to take uh, should be the same value. Okay? So we need to take the approach, for example, this. Uh, so at least if you see the form, you can change the form and you will have this. Okay? And by doing so, you will have and you will get okay. So you need to review calculus 1. If you feel you have problem with calculus 1, you need to take much effort to review that. Okay? Because if I have time during this course, I will review some of them, but I think I will not cover all the calculus 1 method. Okay? So it depends on you. Okay? And also one note that I'm at Tuesday class, at the end of the class, I show you some solutions for some number. But I think I forgot to mention about the arc length. Okay. So if this is the curve, usually parametric or polar, the curve will be having loop. Okay? So they tend to go back to where they are from, right? So if we are from theta equals 0, and then we move here, here, and eventually get back to, and we can say, oh, one circle is 2 pi. If we want to uh, measure the length. Okay, we can say that we want to measure the length from 0 to 2 pi. But remember, there is a restriction. Okay? There is a restriction. If you take a look at the formula, okay, at least for polar, you have this formula. What I want to show you is the all the math problem or the calculus. Okay, it's not about the how you are using the formula, but how you understand why the formula is looking like that. Okay, so okay, so the square root. Okay, first is the square root. Okay, where does the square root comes from? The square root, it's come from the Pythagorean theorem. Okay, so if you see the graph, for example, I take this as my curve. If I want to observe this area, or maybe make it a little bit long, this triangle here. Let's say this is the L. We have the x and the y. Okay. So the L will be square root of dx squared plus dy squared. Okay. And then you know from what we have done before, we can manipulate the form and we go back to this polar arc length. Okay. Now we have the integrations. What does that mean? Okay. The integrations means you have this DL. You are adding all the DL from initial point to some point. Okay. Depends on what the integration is. Okay? So you are plus this DL. So for example, you have DL here, plus, 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 plus. Okay. And remember, the integration, as by definition, is area under curve, right? But here, it's like the area, but we are restricted the area in a form of length. But it's actually similar to area under curve. Okay? So what will happen if uh, we look at this curve? We are measuring here with plus, 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 plus. But until here, we suddenly minus. That's why when you apply the formula from 0 to 2 pi, you will get 0. Okay. Does that logic make sense? Okay. So to approach this, you need to approach from 0 to here, to pi, and then multiply by 2. Okay. So the restrictions say that the curve should traverse once. Okay. That's just a small notes for the arc length. Okay. And I will upload the rest of the solutions maybe next week because some of the students they are not coming to the quiz because some problems. So I need to take them to another exam. So I will upload the solution next week. And for today's course, actually I want to go through the 11.3. 11.3 is the, let me write here. By the way, who hasn't take the quiz? Is there any of you? Okay, and now you have to take all the quiz, right? 11.3. It's the title is integral test and estimates of sums. Okay, we begin with the sum of 1 over n squared. If we expand this sum, okay, we'll have 1 plus 1 over 8 plus 1 over, let's say, just make it 2 squared, 3 squared. Let me make it 1 squared. And that. Okay, if you see the curves, if we plot the 1 over n squared, or let me just write in x to remind you what we have done in r plus 1. Let's say this x and y partition. Yeah, I think this is better. Or maybe I will make it longer. Let's say this is the area 1. Let me mark this as 1. And this is area 2, area 3, area 4. Yeah. Let's say just 4, and it's actually having more, but I think it's too small. But this you can see from the picture that this is the area under the curve, okay? Which means based on calculus 1, we already did define the area under the curve with the integrations. So sum of the rectangle is 1. Let me write one more time. Okay, so if we exclude the first term, we can also write down the integrations from 1 to infinity, in which this is 2. I believe this is the calculus 1 lecture at the very end of previous semester, right? Near the end of this semester. So we can define that from this 1 over x squared, it will be converged to 1. Okay, it will be converged to 1. And how to solve these terms with infinity? We are using limit. Okay, remember? Then from that conclusions, because in actual terms, this is 1 converts to 1 with limit, right? So if we are looking at the real what is happening, it's actually maybe 0.99999, right? Remember that? So we can write from here because it's with limit. So the sum is actually less than 2. Or we can write this and the exact solutions is pi squared over 6. But this is different context for what we will going through. Okay? This is proven by Euler. Okay. But at least for this course, okay, the definition up until that the real number is less than 2 is enough. That's enough. You don't really need to know what is happening with the pi squared over 6. Okay? And of course, if you want to know whether it's converged or diverged, we still can use the limit. Okay. Okay. Now let's see the other problem. Okay, now we have 1 over square root of n. Okay, now we same way with the left one, we draw the curve. Okay, let's see if I can draw the curve. Okay. Maybe it has bigger gap. Maybe like that. If you remember that this kind of curve is saying that it's overestimate in integration. So it starts from here. And so on. The total area is greater. So if we add all the area, this total area is greater than the area under the curve. Okay. Because it's overestimate, so it's the value is higher. Okay. Or is greater than the area under the curve, in which we can write down these integrations. But remember, from calculus 1, with the P test, okay, we know that this is actually diverged, right? Divergent. Okay, it's divergent. So because it's divergent, because the area under the curve is divergent, then the total area will be divergent. Does that make sense? Okay. Make sense? So what we are doing here is actually the first one, we are looking at is the underestimate integral. You see the integral having the gap, right? So if you write down the improper integral, so 1 plus the integral from 1 to infinity, if you are using the limit, we know that this is converged, okay, with the are doing it by limit. But if we are looking at what really happened, the sum is actually not really 2, right? But it's still converged. It's still converged. If we compare to the right picture, if we compare to the right picture, if we want to calculate this, okay, and we draw the picture and we calculate area under the curve with integral, okay, from 1 to infinity. We know from last semester with the P series, okay, with the P series, if P is less than 1, like for example, this case, it's half, right? The P is half. It will be diverged, right? It will be diverged. And you can check if you want to draw in the graphing calculator. It has a great gap here, okay? Which means the number is higher. Okay? If you add until infinity, it will go to infinity. Or in this case, we call it diverged. Okay? So because the area under the curve is diverged, then the total here, which means this sum, is of course diverged. Because the area under the curve is already diverged, then the total will be diverged. Okay. So let me write in the good formulations. Okay. Theorem for the integral test. So this is called the integral test. So whenever you find a series, and then you can observe the integral, you can see whether it's converged or diverged. You can have some conclusions. So suppose a function is continuous, positive, and decreasing, on okay, and um, let me write the term sequence in the terms of function. Then series of an is convergent if and only if the improper is converged. So conclusion, if then and if diverges. So the theorem is giving you key information, so on what you should do for this task. Okay? First, you need to see the function is continuous, positive, and decreasing. Okay, decreasing is the I think most important key to decide whether you can use this method or not. Okay. So if you see the function is decreasing, you can check with the integral test. But I think that's not always the case, but at least you can try. So in chapter 11, there will be at least 5 or 6 methods to test the series, whether it will be converge or diverge. One of them is the integral test. Okay. We already did last time. I think the divergence test. That's the very easy testing. Okay, you just need to know the limit is 0 or not. And then now it's the integral test, in which you can take the integral and then it's not really important on how you got the value. At least you get, okay, it's diverge or converge, then you can make a conclusion. Okay? But also it depends on the case. Okay, let me give you the some example. Or maybe before we go, any question from the integral test? Any questions? Okay. So key point, aside from what the function should be, decreasing, another key point will be the integration itself. Okay, this infinity, okay? Improper integral. So you need to remember all the calculus 1 problem about the improper integral in chapter 7. Yeah, chapter 7. Yeah. Okay, let me go through some, maybe a few examples that not really difficult. Okay, that's the series. Converge or diverge. So we need to know first that what is the graph, at least. Okay, what's the behavior for 1/n² + 1? Or you can write in terms of x. That's okay. That's fine. To differentiate which one is the series, which one is the functions, like the integrations, to help you separate the problem. So maybe you can uh, uh, write down the function. So this function is continuous, right? And it's always going down. It's positive and it's decreasing on this. So by integral test, we solve this through improper integral, or maybe usually t, right? Let me just use t. Okay. Now we can solve this integrations. 1 over x squared plus 1 integral. Yeah, tangent inverse, right? Or arcus tangent. Okay. So we can, let me write all tangent inverse t minus tangent inverse 1. So tangent inverse infinity, that's pi over 2 minus pi over 4. It's pi over 4. So it's convergent. Another note about the P series, if you want to review the P series, so if you have, okay, it's converge if P greater than 1, and then diverge if P less or equal 1. Okay, just to make sure, because we also have the same conclusions as the chapter 7 last semester. And important notes about the sequence. Wait, so another notes about this the series, the sum of the series. Uh, the actual solutions is actually not the same. Both are, for example, we know it's converged, but does the value the same? It's not the same. Okay, so you have sum, you have integral. You can have the same conclusion. Oh, both are convergent, but is it the same value? That's not the case. Okay? That's not the case. To make sure that you got my point. Okay. So, like I said before, if let me make notes. So, if some theorems say that they already proved this is equal pi squared over 6, and we know from improper integral this is 1, right? It's not the same. Okay. So but we know both converge, but not the same value. Okay. But how you solve the integration, you just need to review calculus 1, the improper integral. Okay. All the method, maybe some example exercise, all is similar to chapter 7. The difference is we apply the integrations in terms of sum. We need to decide this is converge or diverge. Okay. Okay, that's the integral test. The next one is the estimating the sum. So what does it mean? It means let me write, from integral test, we can showing the sum of some terms is converge or diverge, right? We already showed that. But the question is, can we approximate? Or estimate, okay, the sum? But remember, the S itself, sum, let's say sum Sn, is actually approximated by limit, right? This is we've done before. But then it's not just about approximations, but how good the approximation is, how good the estimation. Now we need to use the remainder, or in terms of Rn, or in a data set or in a statistics, it's called the error. The error. Okay? So what is the estimate value and what is the actual value? Okay? So we can say the Rn is the difference between this, in which you can write down all the terms of an plus 1 plus 2 plus 3 and so on. So Rn is the error when the Sn is used as approximation to the total sum. Let me make some graphs to help you visualize what it really means. But because we are still in the domain of integrations, that means all the integral test restrictions, it's all applied. So we need to see the functions that decreasing. Okay. Let's say this is y of x, y of f of x. Let's say I will write all the area under the curve. And let's say we start from n plus 1, n plus 2, and so on. So Rn is less or equal okay, the more the value is getting closer to the integration value, the error will be very small, right? Very small. Yeah. And then uh, another case we can see. Maybe the case is the case can be overestimated, okay? Which means the R is greater equal. Okay. So we can have these two conditions, okay, when the R is underestimate or overestimate. Okay. That value of over and underestimate is the error, okay, the error. Then we can have some conclusions that the remainder estimate for integral test. So suppose let's say we have the functions in the terms of a sequence. F is continuous. It's the same as the integration history, positive, decreasing for x greater than n. And the sum of an is already converged. If the Rn is the S minus Sn, then let me write in the left part. And less than n. Okay. Okay, this conclusion is came from the graph, okay, the over and underestimate curves. And let me give you an example on how we are estimating the sum. Okay, which means actually it depends on the case. It can be the left one here or the right one. It depends on the case. If the actual value is higher or lower than the curve. Actually, there is proof for integral test, but I think um, we don't really need that. But you can check in your textbook if you want. Let me give you the example for Pro Approximation. So approximate sum of the series one over n cubed by using the first 10 terms. And then the next question is still related. How many terms required to ensure the sum is accurate within. So the error should be 0.0005. Okay, so I think approximations. If you are really looking forward to become a good engineer and will maybe deal with um, some software simulations, I think any logic uh, training for at least statistics, math, they will include approximation, and that is actually good for you. Uh, Even for come with if you have like for example, every if you observe the big equipment in the machine, uh, especially in the big industry, they will have some periods for maintenance, right? And one of the maintenance they need to take is uh, they need to check the vibrations of the machine. Okay? And it takes a lot of money. And to approach the error with a good error, you need to have a good sense of uh, error estimations. Either with the simulations, come with a new formula, new technique, and it still have a lot of possibility to improve. Okay? So if you consider yourself in that area, you can learn more about that because I think the subject or course like numerical analysis, I'm not sure in the MTSC, in which year? Maybe second or maybe third year, maybe second year, the numerical analysis. Or have you learned or have you heard numerical analysis? I think in mechanical or maybe civil, maybe they will have, or maybe something similar with that course. But how to approach the courses is basically approach with the estimations. Okay. Okay, back to the questions here. So first, by integral test, okay, we need to check the integrations. So we can solve this by improper integral. So we need to limit these integrations. Let's say it's t going to infinity, 1x cubed dx. We can solve this easily. It's not complex or complicated. From n to t. Okay, we got this, and if we plug in the t, we get just 1 over 2n squared. Now this is the value of the integration. Now the sum will be, so the sum this is approaching S10. The first few terms, the first 10 terms. Right? So this you may use calculator for this exercise. So this is if we add all the first few terms. And the remainder for the first 10 terms should be less than from 10 to infinity, right? Okay. Of the 1 over x cubed dx. We calculate this based on 1 over 2n squared. It's 1 and 10 squared. Or we say this is 1 over 200. So the size of error is 1 over 200 or 0.005. So if we need to find accuracy within 0.0005, so we need to have the Rn, it should be less than the value itself. And if it, actually, it's just a reverse from the first question. Okay, it's the same thing, but we move backwards. Okay, so we go into Rn less than the integration n So we get 1/2n squared should be less than the accuracy, the 0.005. We solve this and we need to show that the n squared is greater than or n greater than. So we need these terms until these terms to make sure that it's within the accuracy. Or in these terms, we can say we need wait, we need 32 terms, okay, to get accuracy 0.0005. Okay, and we can also modify the formula for the estimation from the remainder. We can modify with the R. Okay. Okay, any questions? Okay. So what you need to do is you just need to see the remainder, see the if it's asking to find the terms, how many terms that it need to take an error, certain error, or you need to calculate the error. Okay. So we can also modify because Rn is S minus Sn. So let me write the n plus 1. We can modify this by uh, moving the Sn. So we can move Sn to left and right. So that we are going to see that we can so Sn is plus Rn is S. Okay. So if we plus Sn, then we can see these relations. So either way, the top one or the bottom one, that's the same thing actually, same thing. So how to find the terms, how to find the error, all the same thing. Okay. Okay, any questions? I'm planning to at least going to 11.4. So 11.3 is the integral test and estimations. Okay. The 11.4 is the comparison test. So first is direct comparison test. Later, I will also upload some exercise for you from the chapter 11. Actually, the problem set for chapter 11 is mostly determining which or series converge or diverge. Mostly, the case is to find converge or diverge. And to solve that, we need to check the method, okay, and check the condition of each series or sequences. Okay, let's observe we have some. Okay. Of course, this is, if you see the form, if we expand the form, we see that okay, it starts from 1/2 and 1/2 squared, 2 cubed, 2, 4, and so on and so forth, right? This is the geometric, right? Geometric series. You are multiplying half, 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 okay? Okay. So we say that this is A is half and R is half. So because this is geometric series, we can say that this series is converged, right? And R is less than 1. If you want to take the sum, it's this formula, right? Half, half, 1, okay? If you want to check this sum. Okay, but nevertheless, this series itself is converged. Okay, now observe. Let's modify the series. Okay. Now you have 1/2 with the power of n plus 1. Okay. Now because we already know that if we look at 1/2 power with the power of n without 1, this is geometric series, which is convergent. Now from here we can compare. So this is where the direct comparison test. So because 1/2 with the power of n plus 1 is less than 1/2 with the power of n. So this showing that it's also smaller terms. Which means this is smaller than 1. So we can conclude that this is also converged, right? Okay. Got the logic? Okay. Make sense? Okay. So if we can prove some, so if you see any formula, any series, and you can maybe prove that, oh, it is less than any convergent series, then you can conclude that, okay, then this is converged. But you don't really need to know how much the value. You just need to know, okay, it's also converged. Okay. It's similar to what we did before, the comparison test. Yeah. Okay, let me write any maybe official words. So theorem, maybe here. So direct comparison theorem. So suppose we have two series, A and Bn. So these two series are series. So these two are series with positive terms. If the Bn converges and An is less than Bn, then An also converges. And if diverge and An is greater, okay? For An both this is for all n. For all n. This is also for all n. So then An also diverges. Okay. Okay. Does it make sense? Okay. I think it's similar to what we have before, the converged diverge. So if you have two series, if one of them, like for example, if this Bn is converged and the An is less than Bn, so of course An cannot have diverged, right? Because the Bn is already converged. So the series of An should be also converged. Okay, but the key is to prove this. Okay, it's true that okay An is less than Bn, and then you can say that okay because it's true, then you say oh it's converged. Okay, and if Bn diverge, you need to prove that the An greater than Bn, so that you can say, oh, okay, An is also divergent. If this is less, what is happening? You cannot prove anything. You need to choose another method. Yeah, that's the idea. So we have several tests. So when you encounter the problem, maybe you check, but sometimes you cannot prove anything. Then you need to change the method, check with another test. And how to know which method to which problem? It's based on the restrictions. Okay. For example, the integral test. Of course, it should be decreasing. If you see any increasing functions, then okay, you can skip the integral test and choose another one. And here, my suggestions: if you see any series that okay, you can think that oh, I know that similar with the formula. I know the other formula that converge, but it's much more simpler. Then you can check the comparison test. Okay. Usually, you can compare with something that already defined. Like for example, the 1/x², the p series is always converged, right? That's something that easy to compare. Okay. So I hope you remember the calculus 1, the improper integral, because most of the comparison formula is coming from the simple improper integral formula. Okay. Okay. Okay, let's check some example. Check whether this is converge or diverge. Oh, by the way, for the integral test, if you want to know whether the function is decreasing or not, how do you know? Aside from drawing, aside from drawing, you can check the tangent using the calculus 1 and find that it is true that it's moving from positive to negative. So it's decreasing. Okay, remember that. Yeah. Okay, back to the example. Actually, from this form, we can see that we can actually uh, observe this, right? Because we know that it's less than 5. Okay. And we can solve this, and it's actually just 1 over n squared. Okay. This is converge, right? Converge uh, the p test or p series, and by doing so, we can conclude that this is converge. It's converged by direct comparison test. Still 11.4. Now there is also another method. It's called the limit comparison test. So it's this similar comparison, but we are using a limit. For example, if you observe the series 1/2 with the power of n minus 1. This is like what I said before. So if this is true that this is converged, right? But this is greater than this, right? So let's say this is the an from previous theorem. This is bn. It's supposed to be an less than bn, but it's an is greater than bn. So we cannot use direct comparison. Okay. So limit comparison test. Okay, so limit comparison test. So suppose we have an, series an and series bn. It's same both series with positive terms. So if limit has an approach effective of the an over bn, it's equal some value c. So where c is a finite number and c is greater than 0, then either both series converge or both series diverge. So we need to compare them in terms of one sequence or one series over another series. We need to take the limit and we need to solve and see whether it has the solution or not. If there is no solutions, then again, we cannot use the method. We need to change other methods. So if we want to test the first problem, test the test whether this is converge or diverge. We can say this in is this. Let's say bn is this, and we can just limit the n approaching infinity and an over bn. So 1/2 n minus 1 and 1/2 to the power of n. We get 2. Okay. Oh, forget the limit. Sorry. So limit n approach infinity and limit n approach infinity. So from here, we know that we can solve this by dividing all by 2 with the power of n. So it will be equal 1. So limit exists, and this is converge the geometric series. So the limit, or not the limit, the series of the 2n minus 1 is converged by a limit comparison test. Okay. So what you need to do is you take the limit and make one series over the other series. Okay. And then check whether they are exist or not. Okay. If they exist, both can be converged or both diverge. But because we already know that this is converged, then the other will be converged. If this is maybe the Bn or An is diverged, then the other one will be diverged. Okay. So the conclusion is both converge or both diverge. Okay, any questions? Any questions first? There are actually similar estimating sum in this 11.4, but I think I'm skipping it because it's actually similar with the integral test, but using different terms. Okay, I think for today's class until 11.4. Okay, so next time we start from 11.5, and maybe next week, hopefully Tuesday or Thursday, I will give you the quiz. Okay, hopefully I can finish this week. Okay, if there's no questions, then class is finished. Okay.